Hey everyone! So electric cars are great, right? Everyone's switching to them. They're quiet, they're eco-friendly, and they are the future of transportation. There's just one small problem. Yeah, this exact moment. Range anxiety is real. Traditional EVs means that you're going to plan your life around charging stations and staring down a dying battery on a long highway.
Right on. Worry not, mate. Cause the future is already here. Absolute game changer. Say goodbye to cables and all that plug-in anxiety. Because we are talking about DWPT, Dynamic Wireless Power Transfer.
Wait, dynamic what? I'm on a long journey here. What are we talking about?
Listen, mate, I'm talking about charging your motors while you drive. No stopping, no queuing up. The power is integrated right beneath the tarmac. As you cruise over it, your car automatically sucks up energy via electromagnetic induction. It's absolutely spot on. Your battery stays topped up the entire journey.
Okay, a road that charges my car while I'm moving? That sounds like an absolute sorcery. I need to know how this works. Let's dive deep into the electromagnetics behind DWPT. Take it away, guys.
Alright, let's continue with the electric vehicle charging challenge. Electric cars are great, but the way we charge them right now with wires has some big real-world problems. First, it takes way too long. Sitting around waiting for a car to plug in and charge for hours ruins travel plans and slow down delivery trucks. Second, drivers get a lot of anxiety. They constantly worry that their battery will die before they can find an open, working charging spot. Finally, building enough plug-in stations is a huge headache. It takes up too much land in busy cities and can easily overload the local power grid. This ties directly into EA4 or Engineering Activities 4, consequences to society and the environment, because figuring out how to handle grid overloads and land use is a massive challenge for our communities. This is why we need a better solution.
Moving to slide 4, charging a moving vehicle introduces highly unpredictable dynamic challenges. As shown on the right, we break this down into 3 main points. First, dynamic conditions EA1, where power continuously shifts during motion. Simulating this high-speed environment requires advanced engineering computing resources, which is why we utilize MATLAB. Second, lateral misalignments EA2 from land swerving. And third, a varying air gap EA2 from road bumps. Both misalignments force us to navigate EA2 by managing the conflicting physical interactions between a chaotic moving chassis and electromagnetic coupling stability. Moving to validate this mathematically, we execute a numerical script in MATLAB as you can see running on screen. The code loops through the vehicle's position millimeter by millimeter. Look at our final curves. The red line tracks severe efficiency decay as the air gap expands to 25 cm, while the blue line captures the sharp drop-off when the car drifts past 50 cm sideways. So this simulation perfectly proves our technical challenges. I will now hand it over to my teammate for slide 5 to present our proposed system architecture. Thank you.
Let's move on to the principle of inductive power transfer. So, how do we fix this? We use wireless charging while the car is moving. The main goal here is contactless power, sending energy through the air without any physical cords. The setup is pretty simple. We use a 2-coil system. We hide one coil under the road surface and put another coil underneath the car. This brings us to EA5, familiarity of issues. Instead of using normal plugs, we are using basic physics principle to solve a new problem. We use Faraday's law of induction. When we send an alternating electrical current through the rod coil, it creates a moving magnetic field. As the car drives over it, this magnetic field passes through the car coils and creates electricity, charging the battery on the go. It is a smart, clean way to use physics to solve a modern problem.
Okay, thank you. Following our system overview, I will now explain the underlying electromagnetics. The fundamental parameter driving this technology is mutual inductance EA4, defined by the formula shown here. As illustrated in our diagram, K represents the coupling coefficient in a moving vehicle system. K is naturally weak due to the air gap when the car swerves or bounces, as I demonstrate in my earlier MATLAB simulation. This coefficient drops instantly, causing our mutual inductance to plummet. To counteract this, we apply EA3, the creative use of engineering principles. We integrate resonant capacitor C on both sides to create a high efficiency magnetic link. This strategy addresses EA5 as we extend beyond standard stationary transformer models to apply a principle-based approach to an unconventional moving system. By tuning the circuit to resonance, we cancel out the leakage inductance, ensuring the vehicle receives stable power regardless of the physical misalignment.
Let's look at the physics making this possible. Resonance. The primary challenge is that air is a poor conductor of magnetic fields, meaning energy from rod coils easily leaks away. We solve this by matching the system's natural rhythm, just like pushing a child on a swing at the exact right moment for maximum height. In engineering, we do this using an LC resonance circuit. At the global EV standard of 85 kHz with a 100 microhenry coil, our calculations show we need exactly a 35 nanofarad capacitor. Balancing this equation mathematically cancels out the air gap's resistance, allowing us to push peak power to the vehicle. This graph shows how we tune the system to the perfect frequency of 85 kHz. By matching this rhythm, we cancel out resistance and maximize power efficiency for wireless charging. So, we move from a perfect math to the real world. Cars bounce and drift, and even a slight misalignment drops that magnetic connection. Instead of digging up actual highways to test these, we use ANSYS simulation software to visualize the invisible magnetic flux. These simulations led to a critical design upgrade. Because standard circular coils fail during misalignment, we engineered the double D coil shape. This projects a wider, taller field, keeping the car charging even if it drifts off center.
Dynamic Wireless Power Transfer, or DWPT, is a game changer that fundamentally redefines the future of transportation. By charging vehicles seamlessly while they move, DWPT enables continuous driving, effectively erasing range anxiety from the consumer mind. Because cars can stop up on the go, it dramatically reduces battery size pressure. Vehicles no longer need massive, heavy, expensive battery packs, making future EVs lighter, cheaper, and far more sustainable. Furthermore, dynamic charging eliminates urban charging congestion at stationary plugs. While it will eventually benefit all drivers, its immediate target application focus on heavy-use transport. For example, buses, taxis, and freight corridors, laying the critical infrastructure required for more fully autonomous smart roads. To bring this technology to reality, engineers must master two core activities. First is design and innovation, which is EA3. DWPT requires novel applications of electromagnetic principles. Engineers are actively designing optimal coil geometries and advanced control algorithms to handle real-world challenges, like vehicle misalignment when switching lanes, ensuring high efficiency even at highway speeds. Second is analyzing the consequences to society and environment, which is for EA4. Engineering isn't just about functionality, it's about responsibility. This activity involves rigorous analysis of magnetic field emissions to guarantee absolute human safety, alongside optimizing grid efficiency to ensure DWPT genuinely reduces the transport sector's carbon footprint.
So for the conclusion, inductance and resonance aren't just theory. They are the pillars eliminating the biggest EV limitations today. First, range anxiety, and second, static charging bottlenecks. Charging on the road isn't just about saving time. By building wireless chargers directly under the driving lanes, we make travel greener, more efficient, and ready for self-driving cars.